Hi guys, up next we've got Anshuman out of San Francisco. Over to you, Anshuman.
Thank you, Hassan. Hi everyone, I'm Anshuman. I'll be talking about the anatomy of an ML-powered stock picking engine. To briefly introduce myself and add some context, I'm an independent trader and machine learning researcher based out of San Francisco. I've previously worked as a sell-side trader in New York and as a prop trader building mid-frequency statistical arbitrage strategies. For the last 3 years, I worked on building an engine that would pick stocks using machine learning to try and beat the S&P 500. So as an experiment, I sent out a newsletter to a bunch of folks with weekly stock picks. I ran it for a year and managed to beat the S&P by 21% as measured from June 2021 to July 2022, which is a period that included large drawdowns in the markets. So I'm going to talk about the engine, of course, but instead of focusing on the machine learning models, I believe it's far more important to highlight the need to build a strong architecture around the model itself. To be precise, there are immense technical gaps one faces when running such models in a production setting. It's important to bridge these gaps regardless of the asset class that you're trading. I know this is going to be a short talk. It could have been longer, but I've only got about 15 minutes. So I'll try and cover some basic concepts around financial markets, market regimes, and so on. I'll move on to the architecture of the engine that I built, how the data was ingested, the feature engineering that I put in place, different issues that I faced in machine learning on the ML modeling front, the MLOps and monitoring solutions that were needed, and the performance bottlenecks that I faced and fixed. Finally, I'm going to briefly walk through the out-of-sample testing with real money that I did from June 2021 to July 2022, after which we'll have roughly 5 minutes for Q&A. With that in mind, let's start with financial markets and regimes. First, what are market patterns? You can think of these as either chart patterns or more complex multi-market time series relationships. Regardless, the idea here is that when these patterns repeat, it's slightly easier to predict the trajectory of the underlying stock or commodity. Now, the basic idea behind regimes is that as patterns evolve through time, their payoffs change as well. So profitable patterns, they might lose their edge or the edge might reappear. And the reason they behave this way is captured by the concept of a market regime, which you can think of as a mathematical summary of where markets and economies are currently situated with respect to each other and to their own historical behavior. Basically, the idea here is that patterns behave differently based on the market regime in place. So with that in mind, market regimes should ideally capture relationships across volatility, interest rates, commodity prices, consumer sentiment, and so on. And these in turn have rich feedback loops that should be taken into account as well. One thing to remember is that market regimes can be as simple or as complicated as needed. For instance, a simple bull-bear regime can be defined as the index being above or below a 200-day moving average. Now, for a slightly more complicated example, in this slide that you can see, I have a market regime model that looks at expected and realized index volatility together and uses these two to condition the expected Sharpe ratio on a 5-day forward holding of S&P 500 of SPY. The idea here is that the more aspects a market regime captures, the more stationary the forecasted dynamics ought to be. Okay, so now let's quickly talk about the engine architecture. The engine that I built can be best viewed as a pipeline with raw market data feeds going in at one end and stock picks at the other end, along with a data layer and a control layer. The ML layer up top on a daily basis processes text and time series data for over 4,000 US stocks, ETFs, macroeconomic series, generating over 1,000 individual machine learning features for each stock. This layer itself is completely written in Python. I rewrote some parts of the ingestion and feature engineering pipeline in SQL to push compute down to the data layer, and I'll talk about that later. In terms of the tech stack, I used standard Python packages such as Pandas, NumPy, scikit-learn, XGBoost, tsfresh, and Hugging Face transformers. The data layer. So the data layer basically consists of the data store to capture clean data post ingestion. I use DuckDB for this. For the feature store itself, I use Redis and DuckDB together. And finally, the artifact store, it's hosted on Amazon S3, where I serialize models, forecasts, regime metrics, and training data snapshots. The monitoring MLOps layer consists of separate Python scripts and Flask apps, and I'm going to talk about that later. In terms of execution, I hosted everything on AWS. I used an R5 2x large instance, 8 virtual CPUs, 64 gigs of RAM, optimized for in-memory compute. The DBs themselves were also hosted on this instance. The engine was scheduled to run 2 hours after the end of every trading day in New York time. Quality checks on the incoming data from vendors were performed. If needed, the providers were repolled. Now let's quickly dive into the data ingestion pipeline. So the engine consumes a wide variety of data. The overall volume, though, is fairly low at roughly 500 megabytes a day. However, data complexity is pretty high. Some feeds are intraday, therefore higher volume. Others, such as earning transcripts, SEC filing, they are unstructured text, therefore they consume lots of space. To top all of this, options feeds are indexed by symbol, put a call, expiry date, strike price, and so on. It's fairly complicated to track. So one thing we should be fanatical about here at this stage is data quality. So even if you get professional data feeds, sometimes vendors might publish bad prints anyway. So a stock whose price is generally $500, all of a sudden might see a print of $2. So you can catch things like this by looking at the implied price changes. And one thing to keep in mind is if this price change is too large, the cost of dinging the data point and waiting for a refresh is pretty low compared to the alternative of having bad data in your database. So once these data quality checks are done, I put in a bunch of columnar compression transforms to squeeze down the data that I use. So for things like symbol names, I map them to categoricals. For timestamps, I store those as pairs of unsigned ints. And I do a bunch of those transforms. So finally, I have an MLOps backup script that picks up these new updates to the data store and saves them to Parquet before pushing them to S3. Okay, feature engineering. So this is really the heart of the engine. As you can see in the slide, each US stock is represented by a feature vector that's composed of bundles of features. So let's start from the very left. So we have raw features that are extracted from feature groups, such as price volume, intraday data, fundamental data, processed SEC filings, options chains, and so on. On top of these raw features, I add basic transforms such as diffs, ratios, logs, percentages, and so on, essentially capturing price changes, EPS changes, and so on. Next, I do some aggregations. I compare a stock's engineered features against its peers in the same sector, industry, index, or within an exhibited co-ownership pattern. So this would be something like if a hedge fund revealed in its 13F filings that it owns a basket of stocks, you want to track that, and you want to capture that relationship. I compute all of these aggregations using percentiles and other statistical metrics such as standard deviation, skew, and kurtosis. I also compare the stock's features against its prior history. So similar statistical metrics as the previous block, but now I compute these on a rolling window basis, where the window itself may vary from 20 days to 252 days. Next, I compute cross-group features. Basically, these are features such as price to sales, price change over sentiment change, and so on. I also compute trading strategy-based features. So essentially anything that would be a technical analysis or chart pattern momentum, trend following, value, earnings quality, low volatility, cross-sectional momentum. So traditional factors, standardized trading strategies, all of these are really features in my model. Finally, what I do is I add market regime features. So these would be things such as changes in the VIX term structure, shape of the US yield curve, how much it has shifted by, changes in unemployment, housing starts, consumer confidence, and so on. All of that is captured in a single feature vector per stock every day. As you can imagine, a lot of information is extracted and captured. So what do we do with it? We build out this forecasting model. So the forecasting model is trained on a rolling window of 250 days for approximately 4,000 stocks. So about 1 million data points in total. This is sufficient to train a fairly complex gradient boosted decision tree model, and I use XGBoost for this purpose. The target for the forecasting model is to pick stocks that have a greater than 75% probability of generating a forward Sortino ratio of more than twice that of the S&P 500 going forward. So I pick the top 20 such stocks and I rinse and repeat every day. I also have a regime model in place that tracks the current market regime and computes forward trajectory projections for broad equity indices such as the S&P 500, NASDAQ, Russell 2000, and so on. Finally, I have a model explainer. That's the Socrates explainer that you see at the end of the flowchart. Basically, the idea here is that it's important to know not just the stock picks, but why they've been picked. I use the SHAP Python package in order to generate these explanations and make them human comprehensible. Next, the MLOps layer, which is super important. This layer, it's really a grab bag of miscellaneous ops scripts and apps, all written in Python. The backup restore module is very simple. It picks up artifacts such as raw Parquet files, serialized models, time-stamped predictions, training data snapshots, and so on, and pushes them to S3. It's sort of like a crude rsync. The workflow monitor, that basically analyzes logs from the main machine learning pipeline. Essentially, it emails me a success or failure report in time so that I can dig in and check what's going on. Ideally, I want to upgrade this to an admin panel. Hopefully, that's going to happen in the future. The feature explorer piece is really cool, in my opinion. My idea here was to have a graphical, visual way of interacting with the features that I compute and see if I can come up with any new ones. So if I do, I can test them in a Jupyter notebook. And if I like my new idea, I throw it into the feature engineering pipeline. Finally, model diagnostics. Since I was building a stock picking engine, I figured it's really important to track model predictions against realized returns, especially trying to see if there are any dramatic gaps in accuracy. Now, this actually happened a couple of times during my out of sample run, once around November 2021 and once in February this year, mostly because of global macro reasons and capital reallocations. So the Ukraine war was a huge component in this. Okay, now performance bottlenecks. The first version of the engine that I built took over 2.5 hours to run at the end of the day. This was very inefficient. So I started looking at a bunch of alternatives to speed things up. The first thing I did was I replaced Postgres with DuckDB. This was a huge boost since DuckDB is column-oriented, which helps a ton when you're doing vectorized computes in bulk. I also use Redis as an in-memory cache to further speed things up. I replaced pandas in data ingestion with PyArrow and SQL. PyArrow to read in the snapshot data, clean it, recast columns, and then zero copy load them into DuckDB. This brought the run down to 35 minutes. The next thing I did was I replaced NumPy with the bottleneck package in Python. This is really a bunch of super fast functions written in C. That saved me a ton of CPU cycles in feature engineering. I also replaced pandas with polars. Now, this is a data frame library written in Rust that's well integrated with Apache Arrow. So the combination of polars, Apache Arrow, DuckDB, and bottleneck helped me bring down the daily run to about 14 minutes, which is overall a 10x speed up. Finally, I'll quickly review the out-of-sample performance of the stock engine and the newsletter service. So I ran the weekly newsletter from June 2021 to July 2022. I used review for that. In that time, on a weekly basis, the engine beats Pi by over 21% with a semi-decent Sharpe ratio, but a killer Sortino ratio of more than 4.5, which indicates really good downside risk management. To sum up, I believe that machine learnings can beat the market. Do I think individuals can build the technology to do this? Yes, I believe it. I did it, and so can anybody else. All right, that wraps things up. Thank you, everyone, for attending the talk.
Thank you, Anshuman, for that. It's just a couple of questions we've got here. Is is it possible to subscribe to your algorithm, or do you run a fund which people can subscribe to for your stock picking?
So 2 questions. So number one, I used to have the newsletter up and running till July 2022. Then I shut it down because the feedback I got was that people were not interested in doing weekly trades. Right. You know, they wanted something that was even lower frequency, which is it's a bit tough to do. The second thing was in terms of running a fund. Not right now. I'm looking at futures markets at this point in time. So I'm sort of shifting gears. That is a whole bunch of other ancillary benefits. So that's what I'm focused on. Yeah.
So another question we have here is, we can see that you're mainly focused on stocks. Is there a way this can work with cryptos? And which data would I need to collect to feed the data engine if I'm working with crypto?
It's a great question. So I did investigate crypto earlier this year for a bunch of reasons. And I have strong indications to believe that this would work in the crypto markets as well. The primary reason is that, you know, each of the assets in the crypto space basically has a unique set of features that propel it forward, right? So that is conditioned on the global macro regime. And the global macro regime is, you know, it evolves independently of individual asset classes. So I am pretty bullish on this being useful in crypto.
Amazing. I think there's one more question which has come through, which is, just bear with me, put it up. Are you able to share results of choosing stocks using your ML engine?
Am I able to? So I don't have the subscription service up and running anymore.
Right.
But the archives are available. So it's didact.ai. People can go in and see, you know, it's timestamped. People can check the performance. But in terms of it, of running it again, I'm not going to go back there.
Sure. And another one which is just coming, how frequently do you retrain models with new data?
Every day. It's crazy, but things change on a daily basis. Regimes shift on a daily basis, you know, overnight sometimes. So you want to be able to capture that.
I think one final question which is coming through is your work open source?
No. For obvious reasons, I'm not going to open source this.
It's a cheeky question. I think that's kind of coming through, but respect to the person who asked that, I think. Look, Anshuman, we've only got a minute left. I'd like to thank you again for taking the time out early this morning in San Francisco to join us. For the community, there'll be a raw recording of this going live within the next 30 minutes. And Anshuman's details are there. I posted a link to the F2F face-to-face breakout room on Discord, where Anshuman will hopefully be joining shortly, and you guys can continue a direct conversation. Anshuman, I'm sure I'll be reaching out to you in the coming weeks to learn a bit more. I was actually in the AI space previously as well, so I certainly found it insightful too.
Perfect. Yeah, sounds good.
All right, awesome. So it's been a pleasure, and I look forward to chatting to you offline.
Okay, thank you.
All right, take care now. Bye.